colleagues will talk about me, so I don't want to go into very much detail into this. But essentially, what you want to do is to set up various communities of practice, very similar to the various societal benefit areas of GEO. And I'll leave it there. With regards to the South African Earth Observation Strategy, what we're trying to do is to maximize the EO investments through coordination of South Africa's EO space capabilities. So if you read the SAG strategy, it's about a coordination, an attempt to coordinate the various data portals in the country. We want to also foster application developments to meet societal benefit needs. And as I indicated when we started off the whole process by getting government departments to articulate the user requirement. And so we have to address those user requirements. We have to link complementary capabilities globally, for example, the GEO. So by setting up the SAIS portal, you also want it to be a node in the group of Earth observation system of systems. So we also want to draw on the GEOS interoperability and data sharing standards internationally with regards to GEOS in terms of data sharing standards, the architecture, and some other principles. So we want to emulate that back here in South Africa with regards to the SAIS portal as well. I'm not going to talk about this, but what we're trying to do here is to sketch the architecture of the SAIS portal, but very similar to what they're trying to do in the GEO context as well. And I think this was the attempt. I'm sure you'll hear a lot more from Hugo a little later on about the SAIS portal itself. So why are we responding to GEO, and what are the benefits? So the benefits to South Africa is that we're deriving value for the development of the SAIS portal. The SAIS portal is a definite requirement in terms of servicing user requirements in South Africa. And so by setting up the SAIS portal, and as we develop that, we want to draw from the lessons internationally as they develop the GEO system. We want to ensure accurate and complete regional data information in global models. So there's a lot of work done in international attempts at modeling. So we want to be able to access some of those complexes. Ensuring the data democracy principles are achieved. As part of CEOS, South Africa introduced the notion of data democracy. And so we wanted to ensure that data democracy is embedded into the whole GEO initiative. And then also to make a contribution to all the DSP grant challenges. Now, there are 5 grant challenges with regards to what we call the 10-year innovation plan. Space science and technology is one. Energy security is the second one. We're now finalizing what is called the bioeconomy. There's global change, and there's human and social dynamics. So those are the 5 grand challenges that DSP has set itself to address in 10 years, starting from 2007. So if you look at all of the 5 grand challenges, you actually need spatial information to service these grand challenges. So there's a benefit that comes to the different grand challenges as well. So what does GEO get from South Africa participating? So it's not just a one-way traffic flow of information to South Africa. There's also learning from South Africa itself. It's creating awareness of developing countries. So as you develop GEO, you have to take stock of what the requirements of developing countries are. It's not just the developed countries that are participating. There's also some valuable lessons from what SCION is doing, the South African Environmental Observation Network, and how you borrow from those experiences into the global initiative. And the SAIS portal made globally accessible. So once we plug SAIS into GEOS, it becomes a node into the GEOS as well. There was the Risk and Vulnerability Atlas was launched a few years ago, and when we presented this to the GEO community, there was a lot of interest. In fact, this was seen as one of the forerunners in terms of the applications. The ARMC is a constellation of satellites that we've been working on. It's been a few years in the making already. But essentially what we want to do is to put a constellation of satellites that will look at the environmental resource management. So, if that constellation is up and running, it will then plow back the data into this particular system. And then also use of the local experts in the international initiative. So, in summary, the SA-GEO is a South African response to GEO and to GEOS. If you look at SAGEO, that's the South African Earth Observation Strategy. It's looking at coordinating and integrating Earth observation activities, which is based on the user requirements. It's also providing access to South African data holdings and linkages to GEO. So as I indicated, SAGEO will become a node into GEO. And then turning to SA-GEO itself, it's a forum for bringing together EOS stakeholders like we're doing today, from decision makers to scientists, data providers to application developers, so that we identify the EO needs and approaches to meet the requirements that we actually articulated at the very beginning. And the NEOS Secretariat is there to support the implementation of the science of SA-GEO. So that's in brief, just trying to contextualize why we're here for the next 2 days. Thank you very much.
Thank you, Val. As Val has indicated, SA-GEO was mooted in the South African Earth Observation Strategy that was written a few years ago, and is there really to start or develop a coordination mechanism for Earth observation activities within the country. This symposium, this conference, is one of the tools that we are using to start developing the coordination, to develop a conversation or to strengthen the conversations that are happening between Earth observation professionals within the country. We hope that this conference is going to become a regular feature on the calendar in years to come, whether it's going to happen on a yearly basis or 2 yearly basis, it's still to be decided. But I think that it's from some of the discussions that I've had with people this morning, there seems to be an excitement about this conference, and the need for this conference has been articulated many times over this morning. Val talked about SA-GEO and gave a little bit of details, but I think that before we get into the plenary session, I just want to give Terry about 10 minutes or so just to outline more, in a little bit more detail, what this animal that we're talking about, what it is, and how we expect it to work. So, Terry, if you don't mind, just I've asked Terry to do this presentation on very short notice. So, thank you very much for that. Thereafter, we will go into the plenary session 1, and can I just ask the speakers if you've to get ready for that? Okay, thank you.
Good morning. Yes, as Imran was saying, this is a very rushed put together to give you just a brief, or really to support what Val has been saying and expand a little bit more on what SA-GEO is and what NEOS is. The first couple of slides I'm going to skip over because I think Val has covered the GEO part of it, or the SA-GEO part of it in detail, and I'll just concentrate on who NEOS is. The Earth observation landscape, I think we have seen. I think the point we want to make here is that Earth observation is very clearly defined by GEO as space, aerial, and in situ observations. And we need to remember that, and when we look around us, we see most of us sort of equate Earth observation to spaceborne Earth observation. And our big challenge is to bring the aerial and the in situ Earth observers into the community as well. The SA-GEO, just to touch a little bit on the basis of communities of practice. SA-GEO will work very much on the organisation of communities of practice. And the community of practice is defined as a group of people who share a concern or a passion for something they do and learn how to do better as they interact regularly. Quite a mouthful. But it really brings together a community that works around a certain objective or interest and works together on that. The characteristic of these communities of practice is that they're self-organizing, so it really comes from the community themselves. They're informal. They are not within any organization, so they cross organizations, and they have many kinds of members. It's not only researchers, but there's contributors, there's facilitators, there's practitioners. They all belong to the community and are active in it. It is all voluntary. A lot of it is based on trust, especially when you start sharing intellectual property. And the real objective is to share best practices and to reuse knowledge by sharing it within the community. The other important thing is that it's not just a talk shop. A community should work towards some sort of deliverable. And what we'll start doing with the SA-GEO is start stimulating and creating these communities of practice. The portal has been explained quite a lot. Getting on then to NEOS as the Secretariat to SA-GEO, Val has indicated that it is a DST initiative. It is a response to the South African Earth Observation Strategy. It was resourced in December 2012, so this is our really first big event, and we hope it goes well. Currently, NEOS is hosted at the CSIR in the Strategic Initiatives Implementation Unit. We're being incubated, they tell me. So when we hatch, I'm not quite sure what will happen. But we're really at pains not to be seen as a CSIR institution to maintain our independence. So in spite of having all our infrastructure and our identity within the CSIR, we are in fact trying to keep an independence as much as we can. And then we're also not to be confused with the South African National Space Agency. I've heard quite a lot of comments saying the SANSA-NEOS conference. There is also an independence between those two organizations. Our vision then is to create a vibrant, collaborative and well-coordinated Earth observation and space applications community with ready and open access to Earth observation data and imagery for South Africa. So that's what we're working towards. At the moment, we're concentrating on the Earth observations. The other sort of space-based communities will come later, and I think Val also mentioned that. The mission that we've set ourselves to be an effective and coordinated initiative for Earth observations and space users, to create and support vibrant, well-coordinated and efficient user-provided forums for Earth observation, and later on again the other communities, and to encourage free and open access to Earth observation data, actively promote international participation, and relevant activities by South African Earth observers and space applications communities. And so in essence what we do, we are the Secretariat to SA-GEO. SA-GEO is the people in front of me, you folks. So we try and coordinate communities of practice through workshops, symposia and meetings. We promote data access and sharing through the portal, and you'll hear a lot more about the portal as that becomes online and starts growing. We establish communications with and networks within the SA-GEO community. We determine user requirements, so the communities identify the user requirements, we promote them. Promote South Africa's participation in international and Earth observation initiatives. It's also one of our functions. And then in future we look at the other communities. And I think very much in brief, that's who we are. I hope that's what Imran wanted me to convey to you. And those are our contact details there. Thanks, Imran.
Thank you very much, Terry. Is this on? Thank you, Terry. Exactly what I had thought you would do. as we go into the next session, let me just get my program, which is titled "The Future of Earth Observations in South Africa." Val has pointed to, in his presentation, to the fact that humans are having an increasingly bigger impact on the Earth and its environment. And this has huge importance for us and our own sustainability, our ability to be able to address issues like poverty and food security and other such type of human endeavors. In fact, humans are now becoming the largest force in the movement of sediment on the globe. Our global hydraulic cement production is something like 2.2 gigatons a year. And just to give you an indication of what a gigaton is, the Great Wall of China is about 0.4 gigatons of bricks and stone. We mine 8 to 9 gigatons of coal a year, and by 2030 this is expected to reach around 13 gigatons a year. This is equal to the total sediment that is delivered by all rivers on the globe. So we're becoming an important and a very significant factor in shaping geology on the Earth. We remove mountains, we've contributed to the nitrogen cycle, we've contributed to many Earth processes. Earth observations is therefore becoming an increasingly important tool for us to be able to derive the information that we require to make decisions around the planet. And like every other nation in the world, South Africa has to take its position and place in this global community around Earth observations. And I think that this first session is shaped around looking at what it is that South Africa is doing and will be doing in the future to address the issue around Earth observations so that we are able to provide quality information to decision makers so that their decisions are supported by evidence. By evidence. The first session, therefore, has a number of speakers. The first person that I'll call up will be Dr. Sandile Malinga, the CEO of the Space Agency. We will also have Lee Anamalai from Miraka, the Miraka Institute. The SACNAS, Dr. R. Becker will be talking around SACNAS. Then we will look at Earth observations and the NGI by Aslam Parker. And the last two presentations will talk to what we've seen up before, the Earth Observation Data Center, as well as the SIOS portal by Paida Mangara and Wim Hugo. So without further ado, Sandile, thank you. Can we give Sandile a hand?
Thank you very much. It's a pleasure for me to be here today and present to you the National Space Program. This is an ambitious plan that was developed in consultation with yourselves. A good number of you participated in the process. It's currently in draft form, and I'll go over it just to present the key points of it. The consultative process involved 4 expert groups, each consisting of about 10 experts in the area of Earth observation, space science, space operations, and Earth observations. Some of those groups also had subgroups that were supporting them, and there was
was also broader stakeholder forums that were undertaken. In terms of the consultation that was, sorry, there's something wrong with this. Okay. In terms of the consultation that was undertaken, there was altogether about 40 meetings of the expert groups, which, as I indicated, consisted of about 10 people each in the 4 different groups. And there were 5 stakeholder forums that were undertaken in different areas of our country, in CapeTown, Johannesburg, or Holiday, KwaZulu-Natal, and Northwest as well. And there was also an online consultative forum or workspace that had about 260 people who participated on it, and a number of other engagements that we had to come up with this program. What exactly does the NSP seek to do? Val spoke about the National Space Strategy, which was approved by Cabinet in 2008, together with the National Implementation Plan, which was developed by the DST in 2010. And both of these documents indicate that the South Africa should have a national space program. And so the exercise that we undertook was to try and define what that national space program should be, and to provide, for the DST in particular, as the line department, clear actionable objectives for the implementation of the national space strategy, and to provide and come up with detailed projects that will be undertaken so as to define funding priorities. At the moment, the way we're doing things is very ad hoc. There are a number of proposals that I receive on the table, that the DST receives on the table. As much as these are good in themselves, they're not coherent, they are not necessarily aligned to what we want to do at this point in time. And so we believe that the NSP will more or less define what the funding priorities are as we go along. And we want to develop through the NSP action plans, timelines, and the interfaces between different stakeholders in the landscape, as well as to provide measurable deliverables that will tell us as to whether we are achieving what we set ourselves to achieve in terms of implementing the national space strategy. Space is a long-term enterprise. The missions that ESA, NASA are undertaking today, I can tell you at that time I was talking to Charles Baldwin, some of those were conceived or approved in the 70s. The Mars mission that Curiosity that landed recently, it's a long-term project that was approved a long time ago. And we also have to move towards that, and that's what the NSP seeks to do. And the way we're looking at this, we are thinking, we're trying to define the first phase of the national space program, what we've defined as NSP 2030, which will take us to the year 2030. The main objective of our first phase as a nation is to establish a coherent, well-defined, and well-structured national space program. We're talking about the projects that we want to undertake, the interfaces between our institutions, and to set a baseline in terms of resourcing of the program itself. And more importantly, every time we go and speak at any forum, people wonder why you're in space. Why should South Africa be involved in space? And so it's very important for us that in the first phase of our program, that we deliver for our communities very high impact, few, if that have to be, projects that will receive the national buy-in and public buy-in and relevance of space. In terms of systems, we believe that we should develop at least one satellite every 5 to 7 years, and globally position South Africa as a community of nations and cement our position in the community of nations, particularly in our continent. You probably know that Nigeria has got 2 satellites in space, Algeria 2, and Egypt probably 2 as well. And therefore, there is a need for us to really take our position as one of the leading countries in our continent in terms of space. The first phase of our program would essentially lay a good foundation for the second phase of the nation's program, nation space program. Another 20 years, taking us from 2030 to 2050, which will be more ambitious, looking at more clearly defined applications and systems and products, and creating a hub in our continent in terms of providing those clear technology milestones that we want to achieve, pushing the boundaries of our technology. And in terms of satellite development, we'll probably move to parallel satellite development, producing one satellite every 2 to 3 years as opposed to 5 to 7 when we start out. Looking at our ambitious program, we are participating in the International Space Station to expand our science programs into biospace and other similar experiments that could be undertaken. How exactly is the program structured? How is the program structured? It's got 4 programs. The National Earth Observation sub-program, the National Space Science program, and then the National Space Engineering program, as well as the National Space Operations program. These are underpinned by capacity development, science advancement, and public engagement, as well as setting up infrastructure, facilities, institutions, and partnerships that are required for the program to succeed. Structurally, we believe that the program will have what we refer to as the National Space Program Core, consisting of a governance and administration core, as well as a core operational core. Here we're talking about the key sensor directorates that should provide support for the program. And then that interface, as indicated there, with the public and other entities that are partners in the program. There are a number of projects that have been defined for the NSP, and I'll go through this in quick succession. Starting with those that are focusing on administration and governance. Sorry. Something's not happening there. I'll skip that. Focusing on the NSP core, here what we're looking at is, as I indicated, the core administration. There are a number of projects that we think we will be pursuing: space coordination and industrial development, space program management, and international partnerships, the operational support which will be provided by the sensor directorates, and then capacity building, science advancement and awareness, and then facilities management of different structures in, for instance, hotech, as well as data management systems that are required. We've looked at the resource allocation or the resource requirements for the program itself, and we believe that these are not what has been committed to by government. It's just the amounts that we think will be required to make the program a success. Currently, SANSA, as an entity, receives about 100 million a year parliamentary grant. And we foresee that going into next year, there will be a marginal increase to about 120 or so of that parliamentary grant to support the cooperation core as well as the governance core of the National Space Program. Moving to the National Earth Observation Program, which is of particular interest to this community. You and I know that the primary objective for the program itself is to essentially ensure that the sustainable development and improve quality of lives of people. When you look at the Earth from space, it's beautiful, and this is what explorers who go to space have seen over the years. But you drill down to Earth, there's pollution, there's extinction of species, as well as many other problems that we're faced with. Looking at Africa as well, in terms of demand in 13.5 hectares per person on our continent. And it's projected that by 2050, we'll be having 1.5 hectares per person on our continent. When you go to ecological footprints as well, the projections are that currently, in terms of ecological demand that we are putting on the earth, we require, as humanity, about 1.5 of the earth to sustain what we require. There are projections that by 2050, we'll be requiring about 3 earth systems.
They have what is called a National Crop Estimates Committee, which produces these official estimates. The members of this committee compose of officials from the Department of Agriculture and Forestry. The Provincial Department of Agriculture officials sit on the committee. The ARC is represented there, and so is Stats SA. And they meet and they put out the bulletins you see on the right there as press releases on a monthly basis. There is also a Crop Estimates Liaison Committee, which is a forum for the general monitoring of crop estimation. And the industry, the economists, the grain traders, the scientists, the government, everybody who wants to sits on that committee and really advises and suggests to the Crop Estimate Committee what they want, how they want the statistics, when they want it, and that sort of thing. So it's almost a sort of advisory committee to the Crop Estimates Committee. And then there's the data providers that provide the information to the Crop Estimates Committee on which they can then base their estimates. There's the National Crop Statistics Consortium, which is a consortium of the Agricultural Research Council and 2 private companies. The Department of Agriculture, Forestry and Fisheries does their own data collection in the form of a postal survey. The provinces bring data to the committee from their observations and their surveys, and even the private sector occasionally puts data into that committee for consideration. The National Crop Statistics Consortium is contracted to try and provide an estimate within a 5% coefficient of variation, so plus or minus 5% at national level and plus or minus 10% at provincial level. So how do we all do this? Now, agricultural monitoring, we know we want to estimate production, and to get production we need a yield figure and we need an area, and if you times the 2 together you get the amount of maize or a crop that's produced. The yield is influenced by the condition that particular season, so your yield is a function of the season or the conditions, and there are 3 aspects to agricultural monitoring then that we need to look at: yield, the condition, and the area. I'm going to concentrate mainly on the area. Later talks will talk a little bit about the yield, and at the end I think there's a drought one that looks at the condition as well. And what I'm suggesting is that Earth observation data is a very superior source of information for the crop area monitoring. So the methodology we follow then is in step basis. We obtain and process imagery in which to create our stratification. We then digitize the crop field boundaries from that imagery. We then do a sampling process. We design a point frame sample over the digitized fields, because that is the most likely area that we are to find crops. We train field workers for observing those points, and I'll illustrate that a little further on. What we do is we do the sampling from ultralight aircraft, and I'll show you that as well. The aerial survey is then conducted. The classification of the imagery is done. Now, from the aerial survey, we can produce a set of statistics because we've sampled the points. While the aircraft are up, they're also capturing observations between the official sample points. And that data is used in the classification of the imagery. And it'll become clear later on that we actually sit with 2 estimates to compare with each other. And because we've done it this way, we can actually produce a crop type map from the classified imagery. And then we generate the results and present them to the Crop Estimates Committee. So how do we use the satellite imagery? The Spot 5 imagery is used for the previous seasons to actually do the crop boundary mapping. So from the imagery we map the boundaries. From those boundaries we then take the sample, and the PISA survey is conducted by the aircraft then. PISIS, for those of you who don't know, sounds a bit fishy, but it actually stands for Producer Independent Crop Estimate System. So we don't ask the farmer what he's planting, we actually go and survey it. The Landsat 4 and Spot 4 and Landsat imagery is used in season, so we look for fresh imagery for that. We use the PISIS data to calibrate the satellite imagery, then to produce the field level crop type mapping. To take you through it, that's the imagery with the boundaries on, and that's the Spot. The previous was Landsat and the Spot, and you can see the slight difference in resolution. And every cultivated field in the country is now being mapped in this way. To illustrate the value of it, when we do this for the wheat cultivation area, the purpose of doing the stratification is to limit the amount of sample points that we need to take. So we want to get our strata as pure as possible. If you have a completely pure strata, you need one sample to get an estimate of the population. So we try and get it as pure as possible. And so we've used the satellite imagery to try and reduce the area where we can expect to find wheat as far as possible. And I'll illustrate that in the next few slides. So we know we make an assumption that fallow areas at a certain time of year is more likely to be planted to wheat than anything else. And so we map out the fallow areas, and that then forms our wheat strata for sampling. Here you can see the bluish areas are the fields that were fallow in February, which is more likely to be the areas that will be planted to wheat that coming winter. Just an expanded view of that. This one just gives you the coverage of the 13 million hectares of cultivated area in the country. The little black lines, if you expand that, are in fact the field boundaries. The value of it has been to us in the reduction of the area that we need to sample. So without having the field boundaries, we would have to sample most of the country, because that's where you would expect to find the crops of interest. But by digitizing out the field boundaries, we now reduce the area which we need to sample by close on 65%. An interesting part of this is that we update the field boundaries on a regular basis. And from the 2007 imagery, which we used for the Western Cape field boundaries, to the 2010, we've actually come up with some interesting statistics on pivot irrigation. There were 2,700 pivots in the Western Cape in 2007. New pivots that were added since then are 1,000. So there's approximately 3,700 pivots in the Western Cape in 2010, where there were only 2,700 in 2007. And the areas are also given there. So one can start monitoring your increase in irrigation, your increase in water usage and things using this type of information. The components of the PISIS system as such, to go through that, is the statistical sample frame which we have. There's a team of observers and an aircraft pilot that fly in the little aeroplanes. The imagery is used, it all goes into a GIS. And then there's some fairly sophisticated technology which the observers in the aeroplane use to capture the observations as they fly over those points. That's the team with their little kits that go into the aeroplane. That's the little aeroplane that I don't think I would like to fly in. But that takes two people, the pilot and the observer. The observer is normally a fairly experienced farmer who can recognize the crops, and I'll illustrate why in a minute. That's the computer screen which they have in front of them with the GPS connected to it. And the point then comes up and they just click on the touch screen to capture whether they're flying over a maize field and some ancillary data as well. That is all directly put back into the server system at SA-GEO, and the statistics can be generated from that. To show you the quality that an observer needs, these are beans, and we distinguish it in soya beans and dry beans. Flying over them from an aircraft, you need to decide which is which. The distinction is these little runners on this one makes them dry beans, where the previous is soya beans. That's sorghum because the leaves are opposite, and that's maize because the leaves are twirled. And that's the sort of expertise that you need in the observers to be able to do this. The collection of the data that's required for the classification of the imagery happens as we fly over these points. And you can see the number of points which are then in the statistical selected sample, and the additional points which are then used for the classification of the imagery. The selection of the imagery is based on the best suitable imagery according to the crop growth calendar, and we've done a crop growth calendar both for the winter and the summer. The colours there reflect more or less the type of colour you see on a colour infrared image, where the red is your green growing vegetation and your more sort of turquoisey is your fallow lands. And if you then put over the best imagery to distinguish between these crops, you get those 5 bands. We normally just use 4 of them because of costs. And to illustrate how that actually works, if you look at those 3 areas, you can actually see the crop calendar going through for maize. From September, it's just sort of emerging and becoming green. October it grows, and then it dies down as we go along. You must please time me. Kick me off when I'm... Yeah. Sugarcane, you get some very useful information on the harvesting of sugarcane. You can see the pivot on the left being harvested on the right. Other way around, I'm looking at it upside down. You can see the development of new pivots. If you look at the comparison of those 2 images in 2.6 and 2.10. And here is an illustration at a field level of how you can actually do the crop type mapping by looking at the various temporal images to distinguish between your maize and your other crops. Yield estimate is done on a subsample of those points, where we actually go to the field, pick the cobs and do the measurements. So just some results of that quickly. What has become very apparent in doing this is that the Free State province is a very good indicator of the national maize crop. In future, we may even be able to get away by just monitoring the Free State, and we'll know what the maize crop is. There's 3 years of different types of seasons, and every time it works out at about 40% of the national crop. The other interesting thing in the Free State is how the wheat, sunflower and maize in the Western Free State differs from the Eastern Free State. Have a look at the column marked average hectares in 2007 and 2008. You'll see the field sizes are noted there at around 40 hectares, and the sunflower and wheat ratio changes depending on the season and the price, whereas the maize stays fairly consistent. However, if you look at the Eastern Free State, you can see the fields are much smaller here, and the wheat changes fairly dramatically, as well as the maize. These are just some examples of how you can then use the classified mapping, the classified images, which has reduced them to district level comparisons. Now remember, we are only sampling at provincial and national level, but because we can do the classification on the imagery, we can actually get a handle on the district level maize area or crop area per district. And just some of the different years, if I just compare them, that's soybeans. And so in conclusion, I think the combination and integration of the various technologies gives us a great advantage. The field boundaries allow us to do the stratification. The Pisces provides information for the verification of the imagery. The crop type calendar allows us to select the imagery. And the remote sensing and satellite image classification then allows us to do the crop type mapping. The future improvements which we need to do, our small field estimation is still an issue. remote sensing of yield estimation we need to work on. And then I just want to mention that we are in fact involved in the GEO community of practice. The joint experiment on crop and agricultural monitoring is one of the projects of the GEO, and we have in fact registered the Free State Province as our GCAM site. So a lot of the research that we do in the Free State will then be shared, and we'll also learn from a lot of the others to apply to the Free State. The GeoGram is a much bigger project funded by the EU, looking at a global agricultural monitoring system. And because we're in a GCAM site, we're also involved in the global agricultural monitoring. And then we look forward to the NSP flagships to further improve the crop type and crop mapping estimation system for South Africa. With that, thank you.
Thank you very much, Terry. Yeah, may I take two questions?
Terry, just a quick question. The field down.
By the Department of Agriculture, Forestry and Fisheries, it's their property. They don't deny anybody using it, but you have to fill in a form and say why you want it. It is one of the sets that needs to go into the SIOS system, and Annalisa Collette is the right person.
And the reason I'm asking is it's very useful for additional modeling for things like bioenergy and so on.
Yes, Bob.
Kerry, I'm interested in the question of stopping rules on observation systems. How good does the system have to be before it costs more to run the system than you gain in terms of economic benefit by knowing your crop estimates?
We have done some fairly rough calculations on that, and I think you can do it for yourself. If you, I forget the exact figures now, but it's about 10 million tons of maize we produce. And if your estimate is out by X tons, you can work out at 1,000 Rand a ton what it will cost to import or export your shortage or surplus. And so by improving your estimate system, you give forewarning about the imports or exports that you need to do, and work out your savings or your cost benefit based on that. And you know, we spend about 10 million a year on the crop estimates, and if you're out by 5%, you're talking of billions of rands that you need to spend on imports or exports. So the more accurate you are, you're literally saving millions of rands. Does that answer what you...
Yeah, the principle I agree with. How you actually calculate what you actually save, because it's not what you spend, it's the difference in what you spent by having foreknowledge.
Yeah.
It's a slightly different question. It's the kind of futures value
Yeah.
that you save. I'd love to see that calculation.
Yeah, I agree, and I think there's a vast field of research in that particular type of area for economists and things to actually do that. It would be valuable.
Thank you very much. I think we'll proceed to our next presentation, which talks about...
This. Oh, Janne. Ja, weet jy ek moet eintlik daai ding page. So ja. Okay. I have some notes written down. Can everybody hear me? I'm going to try and juggle between the notes and the pointer and the slideshow. Okay, I'll try my best. I did some exploring on Terra Modus satellite sensor data products because it is available and it's for free. And I use it to explore some crop estimation methodologies with it. I'm basically going to try and explain the three types of studies that we did using data that Terry talked about just now and their results. And the way forward is basically more like an invitation to the audience to give some recommendations and suggestions as we are in an infant stage of our research. And after that, Nicoline, my co-author, will discuss the stats. We all know the Terra Modus sensor. It's been launched in 2000. It's got data since 2000, And since it was discovered in 1969 that you can use the near-infrared and the red band to detect vegetation, people have also tried to analyze its condition and to quantify it, to try and quantify its photosynthetic capacity. And as an example of this is a 2004 study done in Hungary, where the model's target was to establish a direct mathematical relationship between the satellite data and the yields. For the first two studies, we used the Terra Modis NDVI 16-day data, and for the last study, we added EVI. The objective yield point data set is the subsample that Terry referred to in the talk just before mine. The objective yield data is compiled by the ARC Grain Crops Institute in Potchefstroom, and they do it by placing random GPS points according to the probability strata, as Terry also referred to, and the fieldwork is done at these points for different locations at every growing season. The fieldwork that Terry referred to is they count the copse and the plants and the kernels. They record the planting date, the cultivar, the crop type. They measure the row width, the plant population, and the kernel mass and the moisture content. And this objective yield is done 3 times throughout the growing season. And we worked with objective yield 3, the last one that they do. And the data is collected since 2001 for the 2001-2 growing season. And I think they skipped a year, and then it's up to present. It's been collected. The maize plant has got 10 distinct growing stages, which is reflected by the NDVI and EVI phenologically. The window model is something I developed when I did my MSc. It's a maize yield estimation timing model, and it was used with the normal 2001-2, which was a normal growing season year. I basically developed it to establish when in the season and at what level of confidence you can do yield prediction using NDVI or EVI. The study area for the first study was basically most of the summer maize production areas in South Africa. The second study we used the Free State only. And for the third study we used 5 sites in the Free State. I'll explain it a little bit later. So our input data for the first study was 2001-2, 4, 5, and 5, 6 objective yield data. Our second study we used the 2006-7 objective yield data. And for the last study we used from 2001 to 2010 for dry land white maize fields. And for the first 2 studies, we used the 16-day Terra Modis NDVI composite images. And in the beginning, for the first study, I added decadal spatial rainfall, just to see how it goes. The methodology is very simple. You just extract the NDVI and rainfall values for every GPS point. I just converted the 16-day NDVI data to decadal data just to fit in with the rainfall. And I chose analysis data, which is 90% of the data set and 10% for test data. And then what is basically important in the model is to convert the decadal NDVI and the decadal rainfall data from date to age of the maize plant using the objective yield planting date, which is recorded as I explained. And another important point is the construction of low, medium, and high yields. Low yields were everything beneath 2.5 tons per hectare. Medium yield is between 2.5 and 4.5 tons per hectare, and high yield is everything above 4.5. The results for the first studies was average rainfall and average NDVI distribution graphs. And of course the yield prediction windows, which is the age categories where spectral separation seemed most apparent, and NDVI shows promise for use in yield estimations. It was also found that rainfall during crucial growth stages is more important than total rainfall, so I didn't continue further with the rainfall in the studies. And basically for every year, this is the window periods. So when you put them all together, on average it's day 40 to day 170. You can use NVI and EVI for maize yield estimation. Before I met Nicoline, I can't do stats, so I just did a mathematical accuracy assessment. It's the percentage of times that the NDVI or the rainfall test data was within 1 standard deviation of the analysis data. These are results that I got for the 2001-2 normal year. The graph at the top is the high yield NDVI, the medium yield NDVI, and the low yield NDVI, average graphs. And at the bottom we have rainfall, but I wasn't able to distinguish a specific window for when rainfall was influential in yield prediction. When you use the same method, you get also a spectral separation of the graphs. It was for an above normal year with late rainfalls. And for the 2005-6 year, you also see a spread, but it was also an above normal year with late rainfall. Then we used the Free State data for the 2006-7 growing season. And I basically verified the data for the 2006-7 growing season, which I didn't do with the other data points. I made sure with the crop field boundaries that they fell within, that the modus pixel was within a field, and and I checked it on Google Earth, and I made sure that the data set was clean as it could be, which I didn't do for the previous studies. And we only used medium season growers, which are not short growers or long growers, but in between. And the spectral separation seemed less apparent, but it's easy to explain because there was a study done in 2007 by Germes Heiser where she used my method and she delineated long, medium and short growers that made almost the same curves. So what we might be doing here is actually showing short, medium and long growers which have a direct linear correlation with yield. So that might also be possible. And then lastly, we used our JCAM site in the Free State. We did a small pilot study. We took 45 points at 5 test sites that were vastly different from each other across the Free State. And the objective yield spanned different growing seasons from 2001 to 2010. And for this exercise, we utilized the WAMIS portal. It's a very nice website which shows from 2000 to currently the phenological stages of NDVI and EVI for specific GPS points. So for this data set, I didn't extract the 16-day points. I used the 8-day modus from WAMIS just to see what happened. When you put together all these growing seasons, the spectral separation seemed very less, and the window period is much lower. It's from day 80 to 120 after planting. So it didn't seem like a good idea to combine the growing seasons when you look at the NDVI. And then I went to Morocco and I met Andries Potgieter, Dr. Andries Potgieter, which most of you will know. And he suggested that I use EVI instead of NDVI because it's much more accurate, it doesn't saturate and all of that. So I tried it, and this is basically the results. The spectral separation was a little bit better for the low, medium and high yields. So it does show some promise. And the window period is still very narrow because we threw all the growing seasons together. An interesting conclusion is that the NDVI and the EVI spectrally separate from day 80 to 120 after planting. The EVI has greater spectral separation and less saturation than the NDVI. Maize is particularly sensitive to a shortage of water 30 to 40 days either side of flowering, which happens during decade 7. And the window periods happen to coincide with this critical period. And this is a stage of growth and the effect on the yield. The objective yield dataset is very rich with information, and it was not designed for a coarse resolution remote sensing yield exercise such as we have done on the data. So is it all dressed up and nowhere to go in this environment? There's many limitations on these data when you try to use it as it is for yield in coarse resolution. The NDVI and EVI were compared over different agroclimatological zones. As you can see in the Free State, for example, and different growing seasons for different GPS locations every year. The short, medium and long growers were mixed, and the low accuracies might be due to GPS point and pixel field orientation, field size and mixed pixels. And the standard deviations of the classes do overlap. These are planting date maps. Perhaps we can combine planting date maps and create a long-term NDVI, EVI map for maize of the same age. Will it improve our yield predictions? The statistic results were not very promising at this stage. Another methodology that we might try is to create yield maps in the average window period using the onset of rains. Or we could perhaps try to quantify the anomalies of the current year with the historic years, but then we actually require a long-term time series, like for 10 years, over the same maize fields with their yield figures. These are Schultz's homogeneous areas for possible yields. So perhaps we can use these homogeneous areas to predict yield for. And the study that was done in Hungary found that the high resolution data for field level for 10 meters was more apparent. And the low resolution data found good results with regional and country level. I also think that we should use the area or point predictions made to compare it with the farmers' data, DAF's data, and SAGE's data, if we do it for area estimates for regions or districts. Seeing that the objective yield data is collected anyway and the MODIS data is free and it shows some promise, shall we continue the research, or if the horse is dead just now?
Multilinear regression with NDVI, EVI values used to predict yield. How did we do that? Sorry for that. Okay. Planting date and NDVI dates are synchronized. Data is grouped into 11 and 22 NDVI groups for the 16th and 8th NDVI days and 22 EVI groups for the 8th days respectively. So the data set with the NDVI groups for the group 1 to 11, that means from day 1 to around day 176, and the other groups from 1 to 22, and it also from day 1 to about 176 day, and the EVI as well. Its representation looks similar like this. Okay, and the multiple linear regression with the NDVI, EVI values, how was this done? With forward regression analysis, the variables in the model used is first the different NDVI groups, EVI groups. So in the one data set it was group 1 to 11, and the other data set group 1 to group 22, depending on it, even if it was I-day NDVI or EVI or 16 NDVI, EVI values. I also calculated the NDVI and the EVI, the maximum values fitting a parabola on that data. And I also calculated the NDVI, EVI period of the parabola, the optimum period. And I also calculated the area 1, which is the area of that curve like fitting a parabola. And the area 2 also I did a more accurate area calculation with the trapezium method. The results obtained for the first data set, which was 2006-2007, that was the 11 NDVI groups, which was the 16-day NDVI groups, which was calculated from G1 to 22. In this study, I've got 2 to 5 values, which is good for the estimation. The first I divided here also in high, medium, and low yield areas prediction. But like Celeste said, this was not differentiate very good if you divide it into those different yields. If you look at the total model in the prediction, the area of the real area of that curve came in, and the stage 9, 10, and 11, which is near matrix stage, and it gives you R square of almost 50, which is for this real prediction, it's not bad, seeming that you only use NDVI values for the study. But in the different sections for the high yield, medium, and low yield estimations, it didn't give very good R square values. Okay, the second data set was a data set. Okay, the previous one was only 1 year, 2006-2007. This one is for different years. We also use only the Free State. And, but in this data set, it was better differentiated into these 3 groups, the high, the medium, and the low yields. But unfortunately, we did not have much values. In total, we have around about 42. Which is not good if you do a statistical analysis doing multiple regression. You must at least have 30, it's statistical calculated, to give you a good estimation. So that is not good, so much good. The high yield area gives you also, you see, that gives stages like growth 2 or 4 or 5 in the model, which actually I don't think it must be like that. This one, we put in the optimum period in the model, the growing stage age 30 and 20, which seems more reliable, and it was 63. And the last one, we only have 3 n values, which is not actually, you can't do a linear regression on that, but anyway, we did it. And when you group all these data together, the model did not give a very good R square, because in this model, particularly, it was better that it was divided in 3 groups, because it was also seen in the slides that Celeste showed that it was better with the 3 different groups. Okay, the EVI also gives similar results. It also gives you R square of 46. You'll see that more or less the same stages in each category comes in than the previous NEVI values, and it gives you R square around about 46, 45, and that one is not so reliable because there's only 3 values. But the overall model was not a very good fit, because this data set we could have rather derived it into 3 categories and the other one in 1 category, because the difference was in terms of the years. That was the main thing. So what is our conclusions? We showed that the data sets got different results. One thing is very important, that the noise on the data sets have to be removed to get better prediction, and the model needs to be further tested against other parameters like forecasted rainfall, soil type, etc. In the future, we must get something like those type of things into a model to really do a better prediction. But at the moment, we have got something, but we need to get more information forward. The model needs to be developed and tested for the land type and expanded we must rather take one field and expand it to a series type of data.
Thank you very much. I think I'll take 2 questions in the interest of time. I think let's spin it up. Any questions from the floor? Yes, Conrad.
I think what's just very important to acknowledge is if one mix time and space in your field data and then do the relationship with EVI, it gets very difficult. If you look at the literature and stuff we've done separate and together as well, once you look at a single place and its regression through time and you have multiple growing seasons, you get very strong relationships. But when you try and apply that in any single growing season across a large area, that relationship breaks down. So until we reach a point where we have multiple years of yield estimates for the same field, we will immensely struggle with this problem. And the limitation of all of this is the field data, not the remote sensing. And we continuously stuck there. I don't know what we can do. Maybe if we get the National Space Program flagship, we can fund field work that's comparable to remote sensing and then truly unlock the value of this to monitor crop.
I think then we can proceed to, thank you very much.
We're going to swap chairs because it's not good practice to have a chairman presenting. There's nobody to shoot him when he goes over time. So while Paida's busy getting his presentation up, he's going to talk to us on agricultural field extraction using object-based classification. Paida, we look forward to it.
Okay, thank you. So my presentation is on agricultural field extraction using object-based techniques. I think it follows closely from what Terry was talking about when he was talking about extracting agricultural fields using digitizing methodologies. And as we are well aware that digitizing can be quite tedious and it's error-prone. So in this particular instance, what I was looking for is a methodology which can at least semi-automate the process to a large extent, given that agricultural boundaries are of key importance to crop estimation and are the basic mapping unit in agriculture management. And in this particular instance, I used area photography, which is flown by the Chief Directorate of Surface and Mapping, NGI, and a Sumbandela image. So I tried to look for home solutions to solve this problem. And I explored a few techniques which are currently available to do the extraction of agricultural field boundaries. These include manual digitizing using GIS, which is, obviously it's fairly accurate, but it's quite tedious and it's an expensive process. I think you've heard it costs in the range of about 10 million to do that. And then we have got the pixel classification methodologies, which includes ISO data classification, maximum likelihood and minimum distance. These have got their own challenges as well, because of the spectral issues associated with that. Then there are edge-based detection techniques which have also been developed to try and solve this problem. And there are a number of techniques which are coming up in object-oriented classification, like region growing techniques. There are also deformable models, which are called snakes, and a combination of the deformable models with the region growing techniques they are called competitive models. And obviously, the subject of the day now is the multi-resolution segmentation, which I'm going to be talking about. The challenges of using the pixel classification methodologies include, obviously, the crop phenology, the spectral differences which arise because of this cause major challenges when you're trying to map agricultural field boundaries. the soil moisture within the agricultural fields themselves. Obviously, the spectral differences arise, which makes it difficult even to map agricultural field boundaries accurately. And obviously, the effect of this soil background and pixel spectral variability within each particular agricultural field or agricultural parcel. Then, why am I looking at object-oriented classifiers? I think they'll be able, to a large extent, be able to eradicate some of these challenges which I talked about, which include the utilization of both the spectral and contextual attributes to assist the classification process. And obviously, we think the object-oriented classification is able to segment the agricultural parcels into homogeneous patches, which might be of advantage in the classification. And if we successfully develop rule sets to do this, we hope they'll be transferable enough or they can be tweaked to apply in other text areas. And one key advantage of this is the ability of object-oriented classification to generate GIS ready vector results. So ideally, these are some of the advantages which you get probably using object-oriented classification. So the key objective of this study is to assess the potential of object-oriented classification to delineate agricultural field boundaries using symmetrical set and multi-spectral imagery from CD and TI. So how the most important thing to highlight in this particular study is I tried by all means to stay away from the use of spectrum. Traditionally, the mapping in remote sensing focuses a lot on the use of spectral methodologies. And in this particular instance, I tried to use the geometric properties of agricultural field boundaries to map them successfully. You realize in most instances, agricultural fields, they've got regular shapes, which include circles and rectangles. And that is just that property which I was trying to exploit in this particular instance without the use of spectral properties. And I used a multi-resolution segmentation approach to do this. So there, I tried to increase the influence of shape in the segmentation process itself, so that I think we wanted the contribution of shape to play a major role in partitioning the image into homogeneous patches, which agricultural fields, and so that we could exploit the rectangular and circular nature of agricultural fields. And my first test area was here in the Western Cape, close to CapeTown, in the peripheries of the town. And I was able to segment this area of photo. So you can visibly see that the multi-resolution segmentation, to a large extent, is able to partition the agricultural fields right on their edges. And from there on, what I went on to do is then to see the particular threshold at which the agricultural fields are able to separate from the rest of other pages. And using the rectangular shape parameter to extract, to actually classify the field, I was able to classify the highlighted fields in green as agricultural fields. But then what you also see is within the urban area, parks have also been classified, and they're not necessarily agricultural fields. So that's one challenge. And these are just the preliminary results of what you get if you're using the rectangular shape parameter. And for the circular fields, if you use the elliptical property, you will be able to highlight them to a great extent. Here, I attempted to segment symbolic imagery, as well to see the general outlines of agricultural fields, and what you see, of course, to a very great extent, the borders or the edges of the agricultural fields are well delineated. But then, as you probably see as well, it's not all fields which are really rectangular. So then that brings additional challenges to how you can classify them accurately. Here in this particular case, what I was just able to do is to just demonstrate the effect of the segmentation, that once if you have an accurate segmentation, then you can just export it as a vector file. And this is what you get out of the segmentation from segmenting this particular set imagery. You still see the circles, but then the number of pages which you see there, which are not regular, then definitely they're not agricultural fields. So, using the elliptical and rectangular properties, you will be able to classify a few of the fields, but then still we have got some fields which are rectangular and circular, which are not properly classified. This is due to the effect of the segmentation, which is not perfect. In this particular case, there is a lot of over segmentation, so those particular fields are not picked up because they are not segmented properly. So this work is still in its preliminary phase, and the next phase obviously is to refine this classification and validate it with ground truth data. And from Terry's presentation, I already know the source where to get the ground truth data through his digitized field boundaries. So, what are the key outputs of this study? I think the study highlights that obviously geometric properties can be exploited usefully to extract agricultural field boundaries. So in this particular case, I have not used spectral properties at all. I've just used the geometric properties of agricultural field boundaries. And that's obvious. Then the next thing is, I think such approaches they demonstrate that it is also feasible to semi-automate the classification process, particularly if you're just using, if your segmentation is next to perfect and you're using shared properties, the variability in terms of spectral variance which you normally get is minimized. And the next point is that it illustrates the value of object-oriented classification in agricultural mapping of field boundaries. But then there are also limitations. As you could see, I think parks, they are being segmented and highlighted as agricultural field, or anything which is regular is being classified as an agricultural field. That's a limitation of the study. And the next limitation is there are a number of fields which remain unclassified because of the effect of the segmentation, which needs to be improved. Then with the use of object-oriented classification, it is also possible to use the neighborhood relationships to classify objects. So I would think in terms of the refinement of such classifications, it might be useful to use the neighborhood relations to eliminate pages like parks within urban areas, then, so that you can start to clean up the classification. But then the overall conclusion is, I think there's good potential to use geometric properties to classify agricultural field boundaries. Thank you.
Thanks. Question? Conrad?
Yes, I think, you know, us as remote sensing scientists, we set ourselves up for really tough competition, and that's competing with a human operator to delineate something like field boundaries. And the question is then, how far are we from operationalizing something like this, where the output is truly useful? And I ask that to Stuart.
We need to work together with the agricultural community to see how can this integrate together with yield data, and try and take a look at perhaps combining the structural information, so your texture, your smoothness, together with your indices. NDVI is known to saturate at higher leaf areas, and they can actually try and negate that and see that you don't get a saturation. I don't know if it will do it, but I think it's definitely something worthwhile exploring and to optimize a processing chain. This data is still quite difficult and inaccessible to get into. It's not something that you can immediately open in ERDAS and immediately point and click and do what you want. There still needs to be a lot of processing that actually has to take place, particularly when you start taking a look at combining different paths and blocks and different orbit paths. We have to start taking a look at the geolocation quality control, and that is, I think, something that we're going to be taking a look at, and reprojecting the data into a more accessible data format for the average users. And that, I think, is something at SANZA we really want to continue trying and working at, so we can get this data out and let it be used by the community. Thank you.